Hi, so today we're moving on to our new topic. We're talking about nuclear power, starting with what causes nuclear decay and what radioactivity is in terms of chemistry. There's more than one type of radioactive decay, so today's main point is actually going over the 4 types of radioactive decay that you need to know. We're going to start by reviewing what a Bohr diagram is, take our notes on radioactivity, and then there is a video for you to watch on the scientist Marie Curie. I'm going to start with a little bit of background. So nuclear power is a pretty large political topic worldwide. There's a lot of pros and cons to nuclear power. You're going to hear about it in the news, especially with the emergence of the Chernobyl HBO show, which is fantastic. Also, with the 9th anniversary of the Fukushima meltdown being just a month ago, Indian Point closed one of its reactors on April 29th of last month. So it is a topic that is in the papers and you should keep your eye out for it. But how much nuclear power is actually used in the United States? The United States is huge with nuclear power. It's the world's largest producer of nuclear power, and more than 30% of the worldwide nuclear generated electricity comes from the United States. So in terms of nuclear power, the US is at the forefront. It has many, many reactors. I think New York has 5 or 6 alone. New York uses about 30% of nuclear power for its electricity. So about a third of our electricity is produced from nuclear. And one of the cool things about New York is it is a zero emission state, meaning it is not producing carbon dioxide and also sulfur dioxide and nitrogen oxide with its nuclear power, so it is a zero emissions power source in New York. So let's take a step back and review what an atom and a nucleus is by drawing a Bohr diagram for fluorine-19. So with nuclear decay, we're going to be focusing on the nucleus. So taking a look at the nucleus and why a nuclei might be stable or unstable. But for fluorine-19, just a reminder that when you have the -19, this is the mass number. The mass number is protons plus neutrons. If you go to your periodic table, you can look up the number of protons. The atomic number is 9 for fluorine. The number of neutrons is 19 minus 9, which equals 10. And because we're looking at a neutral atom, the number of protons equals the number of electrons. So there should also be 9 electrons, 2 in our first energy level, and 1, 2, 3, 4, 5, 6, 7 in our outer energy level, or our 7 valence electrons. Also a reminder that on your reference table, the electron configuration is in the bottom corner, and it should say 2, 7, which again reminds you how many electrons belong in each energy level. Over the next week or so, we're going to be looking at isotopic notation a lot again, so starting with the one that we just used in the do now, F-19, or element dash a number, is always the element in the mass number. Isotope notation is typically this, so F for the element, or whatever element that we're talking about, we're going to use the element symbol. The bottom number is your atomic number, and the top left corner is going to be your mass number. If we're talking about an ion or something that has a charge, the charge is going to go in the top right corner. All right, onto the new stuff. So radioisotopes. Anything that is radioactive is a radioisotope. It's an isotope of an element that is unstable. And if something is unstable, it's going to decay until it becomes a more stable isotope. And we're going to look at this more closely in the next video. We're going to talk a little bit why some nuclei are stable and why some are not stable. But just a reminder, protons have a positive charge. when you have the same charge next to each other, they're going to repel each other, just like the same side of a magnet. So this is happening inside of every single nucleus. Positive charges are next to each other. There's a certain amount of repulsion. When you get to very large nuclei, so when atomic number is larger, you're going to have a greater amount of repulsion because there's more protons in the nucleus. That repulsion reaches basically a tipping point that makes the nucleus unstable. Atoms with atomic numbers above 82, so I'm not including 82, so 83 and greater, do not have stable isotopes, which means everything above element 82 is radioactive. So a decent portion of the periodic table actually is made up of radioactive material. Neutrons are in the nucleus to help stabilize the nucleus and to provide a little bit of separation between those positive charges. But as I just said, there is a tipping point. Stability occurs when there's a specific ratio between protons and neutrons. It's about a 1-to-1 or a 1-to-1.5 ratio between protons and neutrons, which is stable. This ratio tends to break down with elements above 82 when there's just so many protons and not enough neutrons. So for those larger elements, they're radioactive. Radioactive decay is when unstable nuclei break apart or are decaying. Decaying nuclei are going to release high-speed particles and energy, and we refer to that as radioactive emission. There are 4 types of radioactive decay or emission that you need to know. Some of it is listed in your reference table, which I'll show you in a second. But there's alpha particle decay, beta decay, gamma decay, and positron. These are the different particles that are released during radioactive emission. Depending on the substance you're starting with will depend on the type of decay it goes through. Certain isotopes go through specific decays, which again we're going to look at in the future. We're going to look at the details about each of these emission types. You're going to need a table that is 5 columns by 5 rows with a little bit of room to write in each box. So here we're going to label across particle, mass, charge, the symbol, and the penetrating power. We're going to start with alpha decay. So alpha particles, we've talked about those before with Rutherford's gold foil experiment. If you remember, Rutherford bombarded our gold foil with alpha particles, which is a type of radiation. Alpha particles do have a mass of 4 AMU. They're a charged particle, and here's the typical symbol: helium 4-2. This should have a +2 charge here, or alpha symbol. Alpha particles are low penetrating power. It has to do with the fact that they're a fairly large particle with a mass of 4, so they don't penetrate that easily. Beta decay, so beta particles are much smaller. They have no mass. They have a negative charge. Essentially, they're like an electron. Negative charge. Sometimes we use a beta symbol with a -1, or it can be written as an E, like electron, with a -1 charge on the bottom. It's an odd notation, but this is something given to you in your reference table. Beta decay has a moderate penetrating power. Positron also has no mass. Positron, like the name implies, has a positive charge of a +1. It's very similar to a beta symbol, only again the charge is +1. Again, moderate penetrating power. These two are about the same size, have the same amount of penetrating power. And lastly, we have gamma rays. Gamma rays, also no mass. They're also a neutral charge. We use a Greek letter that looks like a Y for the symbol, and these have very high penetrating power, which makes them that much more dangerous. So in terms of risk, alpha particles have low risk. Gamma radiation is a high risk because they have high penetrating power. So what you need to take away, particularly from this slide, is the penetrating power. You do need to know which ones have high and low penetrating power. In your reference table, table O, it gives you all the other information from the table you just wrote down. So it gives you the symbols, as well as, well, I should say symbols, and it gives you the notation, which we're going to use later. And it does also show you things you already know, like protons, positrons, neutrons. Protons and neutrons can be additional pieces that come off from radioactive decay, hence why they're included in this table. But in terms of radiation, alpha, beta, gamma, and positron are the actual radiation. So from today's lesson, here's what you should have taken away. Unstable nuclei are radioactive. Radioactive nuclei are going to decay and release radiation. There's really 3 types of radiation: alpha, beta, gamma. Positron is technically a subclass of beta radiation, but these 4 types are given to you in table O along with their symbols and their isotope notation. And then the one thing that you do need to memorize is the penetrating power of each type of radiation. If you have any questions, please let me know. Otherwise, have a good day.